Welcome to Hot Chips 18. Session 5, Parallel Processing.
Thanks. Also wanted to mention my co-author, Mark Jones. He's our CTO and the technical founder of this Ambric outfit, and he's the primary inventor of our core technology. So this is the very first public disclosure of our prototype chip that we've been working on for a number of years, its core architecture, and why we arrived at this solution. Product details will follow this fall. We saw that same many-core sea change that Dave Patterson just talked about it, and we thought we'd be a little weird for chip people and actually look at the programming model first. So we believe that that's really the practical solution, is to focus on that programming model first. Then we invented new hardware architectures and circuit designs to enable a programming model. So here's my brick wall slide. Traditional architectures, CPUs, DSPs, ASICs, FPGAs are all reaching limits in ease of development, performance, power, and general scalability. Single CPUs and DSPs can't follow the performance imperative of Moore's law any further with ever higher clock speeds, more elaborate implementations, because they're all suffering from diminishing returns, physical limits, that chart that Dave showed us. These are the medieval suffering workmen from the Tower of Babel, and it's a pretty fair representation of the poor people that are working on the old model. Conventional multi-threaded, multi-core processors won't scale much further. Shared memory bottlenecks, thread complexity, programmer-managed synchronization problems, they're starting to reach fundamental limits too. Ed Lee from Berkeley had some really good, strong arguments in an IEEE computer article recently that talks about this in a lot of detail. ASICs and even FPGAs are getting harder and more expensive to develop. ASICs, of course, have got these really difficult and rapidly exponentially growing NREs. FPGAs are running into static power issues that are persistent and growing as we go down the curve. But even more seriously, they both suffer from this RTL development model, which has got global timing convergence, design productivity issues. This chart shows the gap between real to taped out design sizes and the amount of gates you can put on an ASIC. So our way of climbing over the brick wall is instead to spend transistors on supporting a more practical parallel programming model. So why have conventional techniques hit these barriers? One big reason is synchronous system design. Here's an ordinary synchronous application, an MPEG-2 video decoder. In MPEG-2, you have a number of functional blocks with two parallel data paths that have to sync up at the end. And the time taken through some blocks, such as run-length decoding, varies depending on the data. Well, the classical approach of designing and verifying a global state machine to control all that correctly in all circumstances is really hard. That's because local changes to data path timing breaks the global synchronization. So you've got this complex finite state machine that has to be modified in a global context, and this is notoriously hard to validate. Really hard to scale up in application complexity. H.264 video compression is much more complex even than this. This system diagram is in Ambric's globally asynchronous system of hardware, software, objects, and channels. And I'll explain more about how this works in the next few slides. It has distributed control through its channels, which are inherently self-synchronizing. Hardware channels enable strict encapsulation of software modules, so local changes stay local. This approach is very scalable with respect to application complexity and with chip implementation. And those large global state machines are all gone. This globally asynchronous system lets us overcome those conventional performance, scalability, and productivity barriers to build massively complex parallel applications on a programmable standard part. Our structural object programming model is the foundation of how this all works, and it's where we started from before we even thought about the hardware. Our chip has an array of 32-bit RISC processors and memories that are programmed with ordinary software, and we call them objects. And objects run independently on their own, parallel hardware, not shared or multi-threaded or virtualized. Structural objects are strictly encapsulated. They execute with no side effects on one another, and they have no implicitly shared memory. Ambric objects communicate through a simple parallel structure of hardware channels. Each channel is word-wide, unidirectional, point-to-point from one object to another, and acts like a FIFO buffer. Channels carry both data and control tokens in simple and structured messages. Channel hardware synchronizes its objects at each end dynamically as needed at runtime, not scheduled at compile time, as I'll show in the next slide. Interprocessor communication and synchronization is local and easy. Sending or receiving a word on a channel is as simple as reading or writing a processor register. Since Ambric channels synchronize transparently and locally in hardware, the developer gets high performance with none of that complex global synchronization. Channels provide a common hardware-level interface for all objects. This makes it easy for objects to be assembled into higher-level composite objects. They work the same way as primitive objects, since objects are encapsulated and they only interact through channels. Design reuse is practical and robust with this system. So the result is much easier and cheaper development, and the performance and power advantages of massive parallelism and long-term scalability. How we build these channels is the key to putting the programming model on a chip. And it goes all the way down to the transistor level, all the way down to how we actually build our registers. Instead of ordinary synchronous registers, we use Ambric registers. It's still a synchronous register with data in and data out, but it also has control inputs and outputs that implement local forward and back pressure on the words passing through it, which makes systems using Ambric registers self-synchronizing. And it buffers up to 2 words, first in, first out. Each Ambric register is preemptive in that its operation is self-initiated. So here's a second Ambric register. When the first register has a word on its output and it sees the second register can accept it, it delivers the word immediately without negotiation. Likewise, when the second register sees that word available on its input and it has room, it consumes the word immediately without negotiation. This parallel preemptive behavior lets Ambric registers run at full clock rate, even with forward and backward flow control. Unlike an ordinary FIFO, these push-pull dynamics are self-contained, so they can become hidden and abstract. A chain of Ambric registers is called an Ambric channel. Ambric channels are fully encapsulated, fully scalable technology for passing control and data between objects. Channel stages are entirely local. There are no wires longer than one stage. Ambric register buffering makes a stall propagate one stage at a time, needing no global control and no global timing cycles. The channels dynamically accommodate varying delays and workloads on their own. You can change the length of a channel without affecting the functionality, only its latency changes. Ambric processors are interconnected in hardware through Ambric channels. Objects running on processors are synchronized to channel activity. When an object tries to output a word to a channel that cannot accept it, the processor stalls until it can. Likewise, when an object needs a word of input from a channel that doesn't have one available, it stalls until one is. The small amount of buffering in an Ambric register lets both processors keep running, so they only stall according to the control and data dynamics of the application. Each processor runs independently, responding only to its local channels. That's why local changes have only local effects, because it's an asynchronous system. It also means you can change the clock speed of each processor independently at runtime to minimize power. So you can design your power management purely in software. So we get our self-synchronizing channels with local buffering and an asynchronous system, which is reasonable to program and fast and scalable, all from this Ambric register. Our programming model made us revisit the assumptions that today's processors have always been based on. Traditional von Neumann architecture reads and writes variables in a memory space through a register memory hierarchy. Communication between processors is an afterthought. Efficient handling of streaming data, such as media processing or packet processing, is not inherent in conventional machines. Our processor objective is processing data and control from channels. Memories are encapsulated objects like any others, read and written through channels. Instruction streams arrive through channels. So we made channel communication a first-class feature of the architecture. This makes for very lightweight 32-bit RISC CPUs. We treat channels just like general registers. Even the internal CPU data paths are self-synchronizing Ambric channels. Data and control tokens keep moving through the system, so the RAMs get used more for buffering rather than as a static global workspace. And all of our processors can execute an operation, do a loop iteration, input from channels, and output to a channel every cycle. That means a processor running a single cycle loop is equivalent in performance and functionality to a configurable hardware block like in an FPGA. But unlike FPGAs, the full range of performance versus complexity between pure hardware and ordinary software is easily available, and you use software programming, not RTL. In our prototype chip, a cluster of 4 processors is a compute unit, or CU. It has 2 types of processors. SRD is a 32-bit streaming RISC processor with DSP extensions for math-intensive processing. It has 3 ALUs with full word, dual half word, and quad byte operations, a multiplier, and a barrel shifter. It has 256 words of local memory for its 32-bit instructions and can directly execute more code from the RAM unit next door. SR is a simpler 32-bit streaming RISC used mainly for forking and joining channels, generating complex address streams, and other utility tasks, which enable sustained high throughput for the SRDs. It has a single full word or dual half-word ALU and 64 words of local RAM for 128 16-bit instructions and for data. The CU has an interconnect of Ambric channels. SR and SRD instructions can dynamically select processor-to-processor channels and channels which run in and out of the CU through reconfigurable interconnects. The RAM units, or RUs, are the main on-chip memories. Each RU has 4 independent 1K byte RAM banks and 6 configurable engines that turn RAM regions into objects that stream addresses and data over channels. 2 engines serve SRDs with random access or streams of data. 2 engines stream instructions into SRDs. And 2 are general purpose streaming engines, one for this CU and one for another CU, which gives a CU access to multiple RUs. We combine CUs and RUs into the top-level physical building block called a brick. We make the core of the chip just by stacking up bricks. The number of bricks serves as a measure of compute capacity. Each brick's got 2 CU-RU pairs, totaling 8 CPUs and 13 kilobytes of SRAM. Bricks connect by abutment through channels that cross brick to brick. The CUs and RUs are arranged so that in the array of bricks, we get contiguous quads of CUs and contiguous quads of RUs. Since short channels are more common than long ones, to optimize the cost and performance of each channel, we've got a hierarchical configurable interconnect. First are the local channels inside each CU that you saw in the last slide. Next level up, channels directly connect CUs and RUs with their immediate neighbor CUs and RUs. And at the top level, distant channels, shown in green, are 1 brick long per hop, connecting through reconfigurable switches. These channels are word wide and always run at top speed, each carrying 10.6 gigabits per second. These brick long channels are the longest signals in the core. except for a low power clock tree and a reset. So the physical architecture is very scalable going forwards. According to our programming model, developing applications for the chip is straightforward. No magic compilers, no scheduling, no synthesis. You start with a structure diagram, like the whiteboard diagrams you already use to architect your application. You describe your application as a parallel structure of objects and the data and control messages they send and receive. You divide and conquer the application hierarchically, defining composite objects according to your higher level functional blocks. Since our objects, even large composite objects, are strictly encapsulated with simple common channel interfaces, it's easy to reuse them from a library. Once validated, encapsulation protects them so you can count on their correct behavior. For your own objects, you write ordinary single-threaded code in standard high-level language and/or assembly code and compile. You don't code parallelism in the primitive objects. That's all in the structure. A functional simulator is available to run and do your initial debugging in a software test bench environment on the desktop. Then you run the realization toolchain, which auto-maps all objects onto physical CUs and RUs, auto-routes the physical channels, and creates a configuration file for the chip. And at runtime, the chip's configured by a host or by itself from serial flash, like FPGAs. You debug and tune performance in that same structural model, in the real system on real data at full speed. Unused processors, memories, and channels are easy to use for real-time debug just by copying channel traffic. We've also included a separate, dedicated debug network on the chip, and you can halt, step, restart processors with the usual debug features, plus observe or trap on channel events. So we defined the programming model and the architecture and the tools to get very high performance from a massively parallel programmable chip, and here's the results. Our prototype chip is a medium-sized 130 nanometer ASIC, which has 45 bricks, total of 360 SR and SRD 32-bit processors. Each compute unit runs anywhere from 333 megahertz down to less than 1 megahertz under software control. At full speed, all the processors together are capable of 1.08 trillion operations per second over 1 TeraOPS. All the RU RAMs together are capable of 466 gigabytes per second of internal RAM bandwidth. The performance is supported by the Interconnect's 425 gigabit per second bisection bandwidth, 26 gigabits per second of off-chip DDR2 memory, PCI Express at 16 gigabits per second, and up to 13 gigabits per second of parallel general-purpose I/O. The power depends mainly on how many processors and memories are running how fast. With everything running at high speed, we estimate up to 10 watts. That works out to less than 1/10 of a milliwatt per MIPS. Here's some real execution examples comparing our 45-brick, 130 nanometer prototype chip with a 90 nanometer, 70 brick estimated version, TI's 90 nanometer high-end fixed point VLIW DSP, and a large 90 nanometer Xilinx FPGA. We created our DSP benchmark by implementing the same functionality as 5 published TI benchmark kernels. We got a range of 10 to 25 times greater throughput. And the code is 1/3 the size and much less complex without all the VLIWs set up and tear down. Developing the benchmarks for this chip took 1 engineer a day and a half. Last, you see the chip's multiply accumulate throughput is superior to the 1 gigahertz 90 nanometer DSP and general purpose high-end 90 nanometer FPGAs. So big numbers on raw throughput and small benchmarks are nice, but what about real applications? Here's a video encoding application we created for a customer benchmark. Real-time motion estimation across 2 reference frames of broadcast quality 720p high-definition video. Motion estimation is the most compute-intensive part of video compression. And this benchmark does full exhaustive search, which is much more computationally intensive than the typical commercial motion estimators. The first step in the algorithm is to take the frames to compare along with candidate motion vectors. The frames are buffered in off-chip DRAM, from which the individual 16 by 16 pixel macro blocks are read and processed. The search is done in parallel by a set of identical motion estimation objects that each handle a different region. Data and results are streamed down a pair of channels, one for pixels and the other for the results. This is the top level of a hierarchical design. Each of those ME units is a composite object consisting of 4 calculation objects, which each process one macro block at a time, and a block to collect and choose the best results. Each of those calculation objects is another composite object, assembled from primitive objects that run on the processors and memories. The motion estimator for a single reference frame is shown here. The full implementation has 2 of these, which both fit in our chip using 89% of the bricks. They only need to run at 300 megahertz. Actual sustained performance is 0.46 trillion operations per second, which is over half the theoretical performance available from the over 300 parallel processors that are running at this clock rate. This shows how the architecture and the programming model are successful in delivering very high performance on real applications in a single programmable chip. So, as I said at the outset, we started to look at scalability to overcome the fundamental barriers to scalability in development cost and difficulty, in timing and in power. Our programming model's object-based modularity makes much greater design reuse possible. Its simple combination of objects written in normal software code combined in a hierarchy of block diagram structures makes high-performance design development much easier and cheaper. Our asynchronous system of processors, memories, and self-synchronizing channels with local synchronous clocking and no long wires is really scalable into future process generations. And conventional techniques increase power way out of proportion to performance increase. Massive parallel processors, performance per watt stays relatively constant. This chip and the programming model make that massive parallelism practical to use. So starting from today's 1 TeraOPS, 130 nanometer ASIC, we look forward to long-term scalability, which we can carry in more than one direction. Same area and cost, increased performance from process scaling and custom implementation leads to 65 nanometer parts with 1,000 processors and over 4 TeraOPS. Constant performance in smaller area for applications that need lower cost and energy also opens up, analogous to the low-cost FPGA and DSP families. This architecture is a member of an emerging class of parallel chips called reconfigurable processing arrays. We distinguish RPAs from multi-core conventional processors, which have only a few processors and a shared memory architecture, by having massive parallelism of at least hundreds of processing elements and distributed memories, and a rich word-wide flexible interconnect fabric. So how do RPAs differ? Well, to start with, there's 2 classes of RPA chips. SIMD, which has only a single instruction stream running all processors the same way. SIMD used to be good for media network processing, but modern applications like H.264 and adaptive network intrusion detection get more powerful by getting more complex and less regular. Or MIMD, where every processor has its own parallel instruction stream. Our chip, and also the UC Davis ASAP chip that you'll see later in this session, are both asynchronous MIMD RPAs. They've got cooler animations than we do. MIMD's diversity of parallel control is most effective for today's applications. It's good for many data structures, not just vectors. Its processors can stay busy on any size of data. But previous MIMD RPA chips haven't been very practical to program, requiring the developer to deal explicitly with synchronization and use hardware-type languages and tools. The Ambric chip implements a MIMD parallel programming model with channels that remove the global synchronization problem. Block diagram structures of objects written in standard high-level language sequential code are reasonable and practical to develop. Here's our first chip prototype. It's internally codenamed Kestrel. It's a standard cell 130 nanometer ASIC in a general purpose logic process. It has 117 million transistors The core array cell density is 85%, which we feel is very good. Its core has 45 bricks in a 5x9 array, a total of 360 32-bit processors, and 4.6 megabits of distributed SRAM. This highlights one brick. You can see the two RAM units on the side, pair of compute units stacked in the middle. So to sum up, we believe we've found practical solutions to the architectural and programming challenges that have stood in the way of achieving massively parallel embedded computing. Ambric didn't just put lots of processors on a chip without thinking about how they're programmed first. We started with our structural object programming model, which scales without limit, and designed our silicon right down to the registers to enable it. This access to massive parallelism realizes an order of magnitude increase in the throughput available from a programmable chip in a given silicon processing area. And its modularity, parallel low power, and local timing mean that Ambric's object-based technology can continue to track Moore's law for many process generations to come. Thanks very much.
Yes, hello?
Go ahead.
Yes, I have about 3 questions. First one, do you do H.264 B frames?
I'm sorry, do we do H.264?
B frames.
B frames, yeah, that, for example, is why that benchmark had 2 copies of the motion estimator. Okay. Our H.264 encoder is still in development, but absolutely for top quality, you have to have B frames.
Have you done a complete encoder?
It's in process. We've got the major blocks done.
The chip itself, does it use asynchronous technology deep down inside, or is that a synchronous chip?
It's synchronous at the circuit level. We could use the pure asynchronous technology, like the fulcrum and the handshake. But what counts to the programming model is to be asynchronous at the system level. The Ambric register can provide that asynchrony at the system level while being implemented in a synchronous technology. And so we use a conventional ASIC development flow and made it an easier way to develop the chip that way.
And the last question is, how long does it take to actually reconfigure the chip?
It depends on, there's 4 different IOs you can use, anywhere from 10 milliseconds to hundreds of milliseconds, well, maybe 100 milliseconds tops. You can do it through PCI Express is the fastest, or off of a serial flash is the slowest, or you can use JTAG.
But you couldn't do it on a frame-by-frame basis for a
Actually, you
video.
could. The chip is totally capable of runtime reconfiguration because the processors actually have a mode that I didn't really talk about where they can execute instructions from one of the channels instead of from local memory. So it's the hardware is there to start up and shut down channels and reconfigure at runtime. We're kind of going to walk before we run and get to that after we've got more engagement with users and find out just what kinds of runtime reconfiguration they want to do.
Thank you.
Thanks. Yes?
Hi, Chris Drasanovic, MIT. Couple quick questions. So do your processes support waiting for an input on one of 2 channels? This would be like a CSP alt or a Unix select style operator?
Yeah, it's our model of computation is similar to CSP, but to more precisely, it's a process network with bounded buffers. Okay, so we don't wait for all the inputs to fire. The code just executes sequentially. If it gets to an input, you know, it'll either accept it if it's there or it'll stall if it won't. We have facilities in the instruction set to do non-blocking checks of a number of different channels to fire off a different method depending upon activation tokens coming in.
Yeah, sorry. And the second one was in the motion estimation benchmark, you have a particularly easy case there where the addressing pattern is data independent because you chose to do an exhaustive search. How would it work with a more realistic estimator where you actually use data to drive the search?
Yeah, that's an interesting point, and that was the benchmark the customer wanted to see. We've actually got a number of motion estimators in development, and I don't really have time to go into the detail, but you can kind of cut that problem different ways. One of the things, you know, I think we heard about earlier today is that when you have an architecture like this, it'll run existing algorithms well, but you really get the best benefit by stepping back and looking at different algorithms. And we've actually done quite a bit of work on that on the motion estimation.
Okay, thanks.
Thanks.
When you write a program on this chip, what kind of API or language do you use to describe, communication between objects and the communication topologies?
We'll talk about that in a lot of detail later this fall when the product announcement happens. But briefly, since we internally develop in Eclipse, our development environment API will be Eclipse. Our first language is a strict subset of Java. Obviously, it doesn't have things like garbage collection because it's all static and local, but the channel communications are just classes that are defined in Java. We will do other languages like C, obviously, pretty quickly. Thanks. Yes?
Hey, I have a question on the Gmax you have shown. So your chip is delivering about 124 Gmax versus TI DSP 4 Gmax, right? In an unconstrained power envelope, right?
I'm sorry, the different gigamax in the performance slide.
Yeah, so 124 Gmax versus 4 Gmax by TI DSP C64.
Yes.
But if you take Gmax per watt, right, so your chip is consuming what, 10 watts?
Yeah.
So then it would be about 12 Gmax per watt versus I think TI DSP is consuming less than 1 watt.
I haven't really compared in terms of gigamax per watt. Performance per watt is very, very good because we have a much lower clock rate. But I haven't done the math on gigamax per watt.
Because I think given the power wall everybody is talking about these days, I think Gmax per watt is what people are looking for.
Well, certainly for signal processing, that's a critical spec. Our approach is, of course, we're comparing our 130 nanometer chip against the 90 nanometer chip, so you need to factor that in. In the long run, in terms of scalability, we have to go to massive parallelism one way or another to be able to have modest clock rates and lots of processors. Is clearly better performance per watt. So in particular cases, I don't know, but I think in the long run, it's going to be winning.
Just to add a comment on that, there seems to be some configurable companies similar in nature, like they have 400 processors on a single die. So they claim to have more Gmax per watt. I mean, 30 Gmax or so per watt. So people are trying to compare performance per watt versus,
Sure. I mean, massive parallelism, you can do any kind of form of many processors on a chip, and I think if you do a good implementation in any given process, you're going to have superior gigamax per watt. Since we've started from the programming model first, and we've dealt with the issues like synchronization and a reasonable programming style, then I think we feel that those are going to be the compelling differences between different RPAs.
Thank you.
Thanks. Go ahead, Herman.
Hey, Herman Schmidt from Tabula. Hey, Mike. So from your previous life at QuickTurn, I imagine you remember that in excruciating, painful detail that user designs aren't planar. So
yes.
Have you seen that issue come to the fore at 45 Brics?
To some extent, yeah, and that's why it's got a hierarchical interconnect instead of just a nearest neighbor interconnect.
But even at the second level, it's 1 brick distant, right?
Sure. And in fact, the architecture that this is an instance of has another level above that. You can certainly see how that could scale up. It's analogous to the kind of scaling issues that you have in FPGAs, but since our grain is so large, the number of objects on the chip is such a smaller number of objects that I think we've got a ways to go before we get up into the FPGA kind of interconnect
Last quick
scaling.
question. Is the network statically routed, or is it as per the user design, or is it dynamically routed as per the,
At the highest level, it's statically routed, and down inside the CU processor clusters, it's dynamic.
Okay. Thank you.
Thanks, Herman.
Okay, our next speaker is Gheorghe Stefan from Connex Technology. He's a professor at the Technical University in Bucharest, where he also did his graduate work. And he is the founder and chief scientist of Connex. So.
Thank you very much. What I intend to present you here is our technology called Connex technology, and the core assets of our technology is the Connex array, which is mainly a data parallel architecture. I will start with few numbers in order to show what is how powerful is this machine. This is a machine working at 200 megahertz. It's a low frequency. But we have a performance of 200 giga operations per second. But all the operations are only a simple 16-bit integer operations. Now I have here a clear number. We just measured the performance of this machine, and we have 60 giga operation per second and per watt, which is a very good performance for an embedded system. We have an external bandwidth of 3.2 gigabytes per second and an internal bandwidth of 400 gigabytes per second. The application domain for this technology, the first application domain for this technology is high-definition TV. And I want to show you what is our solution for solving this very hard problem, as you know, of high-definition TV. We call our solution integral parallel machine. What we have is an integral parallel architecture. What is, in our opinion, what can be this architecture? This architecture contains a data parallel machine, which I will describe you as the Connex array, a time parallel machine in which which is supported also by speculative parallelism, is in our chip what we call a stream accelerator. And also, the third characteristic of an integral parallel machine is that the input-output process is transparent to the main data parallel computation. As you know, almost all the computation in high-definition TV is data parallel. But there are some, I can say, corner cases in which we need a pure sequential approach. For this pure sequential approach, we have this stream accelerator, which solves, for example, as you know, for H.264, the input stream can be decoded only in a pure sequential computation. And for this kind of computation, we have this stream accelerator, which is a time parallel machine, which has speculative features. Now, I want to present you shortly the Connex array. The Connex array is an array having 1 kilo processing elements, simple processing elements, organized in an array, and 2 controllers. One is called, we call it, is a sequencer, which is a stack machine, which is designed to issue in each clock cycle an instruction which is executed by each processing element into the Connex array. But the instruction is executed all the time according to the internal state of each processing element. We have also another stack machine called I/O controller, which is used to control the data transfer between the array and the external memory. This allows us to have, in parallel, 2 main processes in this array. It's the main computation and the input-output, the data exchange with the external memory. Each processing element is a very simple machine in which we have a 16-bit arithmetic and logic unit, a Boolean machine, 8 registers, and a small data memory of 256 words, each of 16-bit words. This is our machine. The key of this architecture is its simplicity. And in the next slide, I want to present you how are interconnected these processing elements. We have the simplest possible interconnection network in which each processing element is connected only to the left and the right using only one register. What is important in this application, using this very simple interconnection network, we can solve with no penalties. In this application domain, we can solve the problem we intend to solve. In this case, it's about high-definition TV. I told you they are linearly connected. We have an I/O plan, which it's one of these registers. It's maybe the register R1, I told here. This is an input-output register, which is controlled mainly by the I/O controller. The execution in each processing element is conditioned by one bit, which can be 0 and 1. Each processing element can be on or off. And we have also, it's not represented here, we have the possibility to do some reduction operations. And the result of a reduction operation is stored in the top of stack of the sequencer. I told you the sequencer is a stack machine. Now, how we solve the input-output system. The Connex array is here, and parallel with the Connex array, we have what we call I/O plan. In one clock cycle, a vector of 1,000 16-bit numbers can be stored in I/O plan or can be loaded from I/O plan in Connex array. And after that, I/O controller takes care of the content of I/O plan in order to send the content of I/O plan to the external DRAM, or I/O plan can be loaded with data from external memory. The instruction sequencer, meantime, is used. This is the instruction sequencer. I don't see if it works. Instruction sequencer is used to sequence the functionality in a Connex array. And only during few clock cycle, the two sequencer, instruction sequencer and IOC, interact using interrupts in order to exchange data between Connex array and I/O plan. But these are only physical details. What is maybe more important is to discuss about how a user sees this, our machine, the Connex array, and how this Connex array can be used. From the user point of view, we have an array of 1 kilo per 256, 16 bits constant, 16 bits value. And we can say the data structures is organized in 256 vectors, each vector having 1 kilo components, and each component being a 16-bit number. In one clock cycle, or few times in few clock cycles, we can take a vector, say the line I, and another vector, say the line J, operate between them, make an addition, subtract, a logical function, and put the result in another line. All the basic operations are very simple because the simplicity is one of the main ideas of this architecture. Here it's an example in which we use full vectors. In this case, we can add a full vector with another full vector and put the results in another vector. But what is very important for the flexibility of this architecture, we can have also operation in which we activate only some components of these vectors. Here we have an example in which each other two components are involved in computation only, and the other are not involved in computation. And in this case, we have here, we can say we mark some columns. Here it's a marked columns. The second, the fourth columns is also marked. And when we perform an operation, only the marked components are involved in computation. Here is somehow a regular selection of the components, but we can have also a selection a selection which results making some operations on the content of these vectors. And in this case, the selection is data dependent. We can say we can have a random selection, and only the selected components are involved in the current computation. This feature offers us the possibility to have a very, very flexible architecture and to solve this very complex problem of high-definition TV. We have here an example in our example, I will show you how we solve the DCT, the discrete cosinus transform, on 8x8 small arrays. We can load in 8 vectors. We can 128 arrays, and we can perform in parallel 128 DCTs using this architecture. I will show you the performance in one of the next slide, and you will see that the performance is very important. What is also important when you intend to impose a new architecture is to have an associated programming language. We developed in our company what we call Connex programming language, which is in this stage of development, is very similar with C. We have some samples here. We didn't introduce new kind of operation, only we added to, somehow we developed only new data structures. We introduced the vectors, and you can operate on vectors. You see the syntax is very similar with C. This language can be learned in few days. Any programmer can be fluent in this language. What is important is not to learn this language. What is important is to start to sync the algorithms for this parallel machine using the representation I used in the previous slides. Now, how looks the first implementation of this technology? The first chip contains the Connex array of 1,000 processing elements. You have here I/O sequencer and instruction sequencer. We have a configurable switch fabric which interconnects the kernel of this machine with few CPUs. These are MIPS machines used for what is pure sequential in this function of coding or decoding high-definition streams. We have the stream accelerator. This is a time parallel machine. And all the interfaces for video and audio, a DDR DRAM interface. And we have tape out in a few weeks of this chip in our company. What are the main strategic decisions we made in designing this architecture? The first was to design the simplest possible architecture. This was, and in this case, I have nothing to show for you very spectacular in what we have, because we use simple arithmetic and logic units, small memories. We didn't challenge the technology. We don't stress the technology in implementing this architecture. What is very important that this architecture is fully programmed. It's a programmable architecture. We didn't add it some piece of hardware to solve critical problems. All the problems can be solved using programmable structures. This is the reason for which I used what I called the integral parallel architecture, in which we have data parallel computation, time parallel computation and also speculative parallel computation in order to achieve the performance asked by our application domain. What is also very important, our architecture is tuned to the application domain. We don't have any piece of hardware for functions which are not frequently used. Only for the frequently used functionality, we have some piece of hardware there in our architecture. And this all allows to reduce the area, to reduce the power, and to improve and to have the performance I presented you in the first slide. What is important, we have a programming language which is able to hide all the structural details of this parallel machine. This was also possible because our architecture is very simple. We developed an efficient compiler and a cycle-accurate simulator for our architecture. And what is the most important for this kind of application is to use very imaginative algorithms to implement the standards to decode or to encode the image. I want to tell you the most important things in using this kind of architecture is to redesign, to reconsider all the algorithms. We cannot take the algorithms from the sequential approach and to apply them for our machine. And this is a very important thing in solving the problem with our machine, because we must to adapt all the standards and all the functionality to a parallel machine. And now what differentiates Connex from other parallel architectures? First of all, we have in our architecture all forms of parallelism which are very strongly segregated. We have a data parallel machine which is separated from time parallel machine, and that time parallel machine, which is called stream accelerator, is also able to perform speculative computation. And in this case, we don't care too much about the distinction between SIMD, MIMD, to have sometimes a SIMD machine, sometimes a MIMD machine. If you tune very well this architecture, putting on the area, if you dimension very well the time parallel machine and the data parallel machine, you can achieve very high performance using a programmable structure. The granularity of our processing element also fits with the application domain. We have only 16-bit small and simple processing element. No multipliers, no floating point features, no multiply and accumulate units. Because the frequency of this kind of operation, multiply or accumulate, floating point, the frequency of this kind of operation is very, very small in this application domain. For this reason, we can perform floating point operation, but programming our structure. And I can tell you, if our performance is 200 giga operation per second for simple operation, for floating point operation, we have 5 gigaflop per second, which is more than enough for what we need in our application domain. Also, what is important, we have the simplest interconnection network between the processing element, because the nature of this computation is that the locality principle applies very well. You see, if you have here a big image, something which happens in the higher left corner has no relation with what is in lower left corner or right corner. Okay? And in this case, the computation is very, very local. And we don't need a complex interconnection network to perform the computation involved in video processing. Also, having two controllers, one for computation and one for I/O process, we can balance, because sometimes we can have a very smart input-output process if we are limited, we are bounded by the computation in the Connex array, or if we are I/O bounded, we can use the computation in Connex array to rearrange data inside. And in this case, these two processes of transferring data and processing data can compensate each other depending on how much in each stage of computation we need to use the array for computing or for transferring data. Now I want to show you some performances. Initially, I want to tell you we have, on Connex array, more than 2 gigaops per second per millimeter square. Here, I repeat, we have here 60 gigaops per watt, was estimated when I wrote these slides, but now it's not estimated, it's measured. Now I want to add some other operations. For dot product, if we have two vectors of 1 kilo components, we can perform dot product in 28 clock cycle with the result in the top of stack of the sequencer. DCT, the DCT is performed in our machine in 0.35 clock cycle per pixel. And for sum of absolute differences, another very important operation used in high definition, in compressing data, we have this performance per clock cycle, 0.0025 clock cycle per pixel. These are very, very big performances, but these are maybe not very important because are local operations. What is important is to take a complex function and to evaluate it. And for me, the most important is that we can decode two HD streams coded in using the standard H264, using only 83% of the computational power of this machine. This is maybe a real evaluation of the power of our machine. Okay. Here are some comparisons which shows, here are the Connex and compared for some of absolute differences or DCT with other machines. These are good to see how different is our architecture. Because also the other architectures are very good, but for other application domains. It's very clear for all of us that using DSP in high definition in television, in video application, is not a solution, because in DSP you have multiply and accumulates, you have a lot of multiplication with big numbers, which in high definition TV you don't need. Here you have some numbers, some performances when we decoded two streams in VC1. And we use for two streams only 67% of the computational power of this array. VC1 is simpler than H264. Here is the layout of our chip. You see here it's maybe the main area. It's not very clear if you see what I present. It's very clear where is the Connex array. We have here the stream accelerated for MIPSs and other logics, PCI interface. And we are in the stage of tape out, as I told you, in 2 weeks. Maybe I finished. Okay, thank you. Do you have questions? No questions. Oh, it's okay.
Hi, my name is Kenneth. Just work for R3, and just have a quick questions. So what is your die size, and how you verify your performance on the the CAPET performance, and also the X.264, how many cycles you put it into this performance result? How you verify this?
First about the die size.
Yes.
I cannot tell you exactly the die size,
Yeah, just
but you can use the last slide to evaluate it.
Okay.
Okay. How we evaluated the, because you have MIPS machine there and other, you can have, but I cannot tell you exactly the die size.
Okay.
Not because you don't know, you know for what reason. But now about how we evaluate it.
Yes.
For VC1, all the programs were executed on simulation, and we have a cycle-accurate simulator for this chip. And we counted the clock cycles needed for decoding VC1. And the number provided was 67% of the computational power. Because we have, for each macro block, we can use no more than 409 clock cycles, because we have 8,000, you know.
Right, yes.
Okay, and we, this was not estimated, it was computed. For H.264, we extrapolated the results. We didn't write all the programs, and the number is 83% somehow. And we have a lot of room for making also post-processing.
Okay.
In both cases.
Yeah, those numbers are very impressive, especially those like the motion estimations and all this.
Yes.
Are very, very good numbers. Okay, thanks.
Okay.
Without further ado, our last official talk of the day is Bevan Baas from UC Davis. He's a professor there, currently working on algorithms, architectures, and circuits for DSP. Did his graduate work here at Stanford and was an early employee of Atheros Communications. So go for it.
Only the switch here at this one? Yep, there we go. Good. Thank you, John. Can you hear me okay? Okay. Let me get situated here. Good afternoon. The topic of my talk is the hardware and software of a high-performance and energy-efficient, highly scalable array processor, which we call ASAP, for an asynchronous array. That's pretty dim. For an asynchronous array of simple processors. As you can see from the lengthy author list, there were a lot of students involved in this work, and I want to acknowledge their effort. This was a team effort of a lot of people. My talk is broken into 5 main sections. I'll begin with a motivation and talking about the objectives and the key features of our architecture and chip, followed by hardware architectural details. Thirdly, some details of the chip and measured results. Fourthly, we'll talk about the software side, the programming, and also some details on some applications that we've completed. And finally, I'll conclude my talk. So to motivate our objectives, I'd like to talk a little bit about our target applications, which are computationally intensive digital signal processing and some scientific applications. These type of workloads are typically key components in many systems. They frequently require high performance and have limited power budgets. To solve these problems, typically we feel that these require innovations across disciplines, including architecture, algorithms, and circuit design. Therefore, the objectives of this project were to design a platform that has high performance, high energy efficiency, is easy to program, and by this we mean in some kind of a high-level language such as C, and suitable for future fabrication technologies is another goal. We have 4 main key features of ASAP shown here on the left, and some of the results on the right in a very broad sketch. The first is a chip multiprocessor. By this, we get high performance. Second is a reduced complexity, very simple processing element, and this impacts a number of levels. One of the most notable is the size of the local memories inside each processor, and this enables high energy efficiency. Thirdly is a Gauss clocking style. This is globally asynchronous, locally synchronous. By this, what we mean is each individual processor tile is a traditional synchronous system, but each processor operates fully asynchronously with respect, independently with respect to all other processors. And this means frequency, halting, changes in any type in the clocks. And this enables both high energy efficiency and technology scalability. Fourthly, we have a simple nearest neighbor communication for good scalability. I'll next talk about some of the architectural hardware details. For this part, for the chip multiprocessor, I'd like to contrast our architecture with a traditional high-speed single processor, and also merge this with some of the characteristics of our target applications, which are typically comprised of a lot of smaller tasks. So on the left, we see this cartoon here is showing a traditional architecture with a very high-speed single processor computing a hypothetical load comprised of 3 tasks, tasks 1, 2, and 3. Intermediate data between the tasks is buffered in a large memory. This might go through a memory hierarchy, and we show these buffered data A, B, and C. In the stream paradigm, we have multiple processors. If things go well, and we'll talk about this in following slides, if these processors are able to compute tasks independently, we can map tasks onto processors and achieve higher performance. And we also get the side benefit of, if we have dedicated links here, we can transfer data as soon as it's available in one processor to the next processor without the need for a large buffer. And we may be able to reduce our total global memory requirements. So as I said, one of the requirements for this is that our processors are able to compute the type of tasks that we're interested in. So we started this project by looking at, this is a short list of a lot of applications that we've already mapped, looking at the instruction memory and data memory requirements. Here we see some filters, discrete cosine transforms, 64-point complex FFT, some sorting, square root exponential, and assumed a very simple single issue 16-bit fixed point architecture and counted how many instruction words and data words were needed. We came up with numbers that were significantly lower than what we usually see in modern processors, especially digital signal processors. We found that on the order of a few hundred words is typically enough to compute a lot of these applications, and this isn't counting what would happen if we split these tasks up across multiple processors. Our next key feature that we're going to discuss is Gauss, so the globally asynchronous, locally synchronous design style. As we all know, most chips are designed today with a globally synchronous style. This has some difficulty due to high clock frequencies, poor scaling of wires, and large circuit variations. And also, this does not have the flexibility to allow us to independently tune clock frequencies across subsections of a synchronous domain. Okay, on the other hand, we have fully asynchronous with no clocks at all. This is another possibility we considered, largely due to a much lower level of EDA CAD tool support. That wasn't a good option for us. So we felt that Gauss is a nice compromise. We have the easy design with the local synchronous, and we have the high flexibility of varying clock frequencies across the system as a whole. Related to this wire problem is the communication problem, the intercommunication problem. So as we already said, wires have been scaling poorly in technology generations, and this impacts the interprocessor communication. For a number of reasons, we went with a nearest neighbor communication style, which greatly simplified and reduced the power for a lot of the applications we looked at. Here are 2 block diagrams showing the system. This is a 6x6 array of processor tiles. This is actually what we fabricated. We'll see a die photo in a minute. You can see the data input comes into the upper left processor, and the output is selected from one of the right column processors. This is purely a feature of our test chip. Every processor, including the edges, has input and output ports, but we just tied these off, and this was done purely because of I/O limitation for our chip. Each processor looks something like this. Here are the major blocks. We have a simple processor, ALU, multiply accumulator control, a very small 64-word instruction memory executing 32-bit instructions, a 128-word data memory, which works with 16-bit data words. Each processor has its own clock oscillator. So we have 36 processors, 36 oscillators. There's no global frequency or phase information whatsoever, no PLLs, DLLs, clock crystals. It's purely what you see here. Each processor also has static configuration, dynamic configuration logic, and the interface to adjoining processors is through dual clock FIFOs of 32 words each, and the output can go to any of the 4 nearest neighbors in any arbitrary pattern selectable by software. The input is set at, we have these 2 inputs, we can choose any of the 4 directions. In our current chip, it's at power uptime. So let's now take a look inside the CPU. Here's the pipeline. It's a 9-stage pipeline we can see here. Just want to point out a few characteristics. We have the main data memory here is of course, embedded right into the pipeline. Sort of takes the place of a general purpose register file. We may have seen we have address generators here. The input FIFOs, the 2 input FIFOs are embedded into the pipeline and are just treated as other sources to be selected in instructions. We have a single cycle ALU, 2-cycle multiplier, a 40-bit accumulator, and the data memory for writes, and again, the processor output, which is we can send to any pattern of the 4 nearest neighbors. The processor executes 54 instructions. We, in pursuit of trying to keep a very small, simple processor, we only implement simple and general instructions, and the only algorithm-specific instruction is bit reverse used for FFTs. We did this it's part of the philosophy of this project. We certainly could speed up certain kernels if we added algorithm-specific instructions, but we did this with the view that programmable processors have the greatest value in computing future workloads, which we don't know today. Otherwise, we could build ASICs, and they're always going to beat a programmable chip. So we tried to keep our instruction set very lean, and we mentioned the 16-bit fixed-point data path. The programmable clock oscillators are digitally programmable. The frequencies are tunable through 3 major methods. One is we can digitally program the current drive through tri-state buffers in each stage. The ring oscillator is configurable in either a 5-stage or 9-stage loop. Additionally, we have a clock divider which can divide by 1 to 128 the final clock signal. We have a modified SR latch, so we can do clock halting faster on a time scale shorter than 1 single clock cycle. Measured results from silicon, we found that we could tune the frequency from 1.66 megahertz to 702 megahertz with a maximum gap in our useful range up to 500 megahertz of 0.08 megahertz. We're able to achieve very fine frequency tunability. Let's now take a look at the interprocessor communication. This is a single processor tile. You see the CPUs squished here over on the side. The inputs, as we said, we have 2 major input ports. We can select from the north, south, east, west inputs. These are shared. And the outputs, we can output to arbitrary patterns on the output. This dual clock FIFO logically sits between processors, between an upstream processor and a downstream processor. Physically, it's located inside the downstream processor. That's why I've shown it here. The right side is clocked by the upstream processor's clock. The read side is clocked by the downstream processor's clock. Data transitions across the array, so we don't have any synchronization problems here if we do our timing correctly. A little tricky part is transferring address pointers. To prevent multiple bit transitions at any point in time, we gray code the addresses and before we send them across. We also have a variable number of synchronization registers to alleviate metastability. We felt 2 should be a good number. We have a configurable number from 0 to 5. To test robustness, we operated the chip with multiple processors for several weeks with 0 synchronization registers and didn't observe any faults. And so we feel this circuit is quite robust. Next, I'll present the chip and some results. This is a die photo of the 6x6 processing array. We can clearly see the 6x6 tiles. Here's one tile highlighted, instruction memory, data memory, 2 FIFOs, and the oscillator is just a little speck in the corner. This was implemented in standard cells, completely standard cell, except for the block memories, in TSMC 0.18 micron. It was fully placed, automatic place and route, and except for the oscillator, was fully synthesized. It's not a very aggressive design, and I think that some of the performance numbers we've achieved are more as a result of the architecture, simple architecture. One story I'd like to tell is we actually first built a 3x3 array, and about a week before tape out, we received notification that we had more space available and we could make it a 6x6 array. And so we actually went back, rewrote the Verilog, the global control, the MUX, redid the power grid, beefed it up a little bit, and went through our whole flow all the way to GDS2 ready to tape out, which in fact we did tape out in a total of 10 hours. And I think this is a good illustration of the scalability of this, that we have no global wires, and this is very easy to scale. Some of the key numbers here, 230,000 transistors per tile, maximum speed of 475 megahertz at 1.8 volts. Area is only 0.66 millimeters squared. Again, this is in 0.18 micron technology. Power, executing a typical application mix, which we'll talk about in a minute, is 32 milliwatts per tile. And if we keep a tile perfect, 100% active, our power goes to 84 milliwatts, which is usually not the case in most applications. And finally, if we lower the voltage to 0.9 volts, it operates at 116 megahertz with 2.4 milliwatts typical application power. Here's a photo of our test environment. This is a PC board hosting the ASAP processor. We see a low-speed PGA package, and this is an FPGA board used to interface between a Linux box and the test board. Here are some measured waveforms. This is a simplified diagram of the application we're running here. This was cooked up. It's not a real application. But we can see the oscillator, the processor 1 here on the left, is its clock is here in the yellow. Processor 2 in the red, its clock is here. We see them operating at different frequencies and halting. Under typical application loads, we see, over large applications, we see utilization on the order of 30–40% for non-optimized applications. So typically, we'd see a lot more halting than these cases. What we see here is valid data coming in from a third processor, not shown. Processor 2 wakes up, less than 1 clock cycle, begins at full rate clock, begins processing. At this point, produces output data, which starts up processor 2, which just halted right here. Processor 2 begins processing and outputs its data. Again, we see the valid is a different width, showing us it's operating in a different clock domain, and the output data changes. And this is a measured waveform. Area comparison. Over here, we have the area percentage utilization. ASAP, we focused on making the communication very small, communication logic, memory logic very small, and the basic core occupies about 2/3 of the total core area, which compares well with these other designs. In terms of absolute area, the processor, this is scaled to 0.13 micron, is about 20 times smaller than an ARM processor, a few generations old ARM, about 90 times smaller than a single cell SPE, and over 200 times smaller than a TI C64X. Very rough numbers here showing energy and performance density. On the x-axis, we have peak performance per millimeter squared. These numbers are all scaled to 0.13 micron. Over here is a very crude estimate of energy. So power divided by clock frequency divided by scale, which is meant to compensate for multiple operations per cycle. Very roughly, ASAP performs somewhere between 8 to several dozen times lower energy per operation and with a higher peak performance density. Just want to mention here, we're not taking into account word widths, workload, in ASAP's favor, actually things like full custom logic versus synthesized standard cell. We'll look at some applications here in the next section, which is a lot more realistic way to compare these. Okay, here we have our programming flow. This is very much, we have a shared vision with the earlier talk we saw from Ambric. We program tasks individually. Before we did this in assembly code, and now we have a C compiler, which I'll talk about in the next slide, that we use to code individual tasks. We then link up tasks. We now have a tool in development. Here's a screen snapshot. We have a palette of various tasks. We drag and drop onto this canvas, draw the links however you want them, and this automatic mapping tool flattens this out to our 2D mesh. We have various optimization criteria, including blocking for faulty processors. If we have processors that have a lower maximum frequency, we can put a lower weight task there. And we have other things that we have in development with this. We hope to have this intelligent mapping tool. And we're able to add routing processors if needed, and so forth. Here's a C program. This is actually a functional example of a quartic arc sine, arc cosine. Just want to point out a few things. This is completely generic C with a few exceptions. One is that we implement saturating arithmetic by declaring integers as saturating integers. We didn't use any in this program, unfortunately. The other thing I want to point out is our input buffers are mapped right into our code. They're special reserved variables. So here's input buffer 0. This output down here is being written to the output buffer. Another key point is it's completely invisible to the programmer how this actually executes in real time, which I actually think is a benefit, because there's no notion of stalling processors, frequency adapting, or halting, or any of the asynchronous behavior to the programmer. As long as we guarantee those asynchronous boundaries are robust and the total system is fast enough, the outcome will always be correct. Just very quickly here, here's a list of some of the applications we've mapped. We have a lot of DSP basic blocks, things like square root, logs, exponentials, pseudo-random generators. Our larger applications include discrete cosine transform, which I'll show some of these in a minute, fast Fourier transforms from 32 to 1 K point, K equals 7 Viterbi decoder, a JPEG encoder, and a fully compliant IEEE 802.11g wireless LAN transmitter. Here's our JPEG encoder. Very quickly, let's see, we're running a bit short on time. The 9 processors here, data comes in, and we'll see an animation of this in a minute. Data comes in, goes through a few blocks. Our 8x8 DCT is here, and finally our Huffman encoder. Some numbers up here. This is fully functional on the chip. Roughly similar performance and about 11 times lower energy dissipation than a published version on a TI C62X. This is a diagram of the 802.11a transmitter. It's fully compliant with the IEEE standard over all 8 data rates, includes training symbols, pilot generation, the whole thing. Spectrally compliant, has a number of blocks down here at the bottom, not required by the standard. Fully functional on the chip, 407 milliwatts at about 1/3 of the full rate at 54 megabits. This implementation is lightly optimized, was completed by one student in less than 3 months with a full load of classes and no previous knowledge of this transmitter. Compared with a published implementation on the TI DSP, it was not a full implementation, roughly 5 to 10 times performance, 35 to 75 times lower energy dissipation. Okay, I'm going to show 2 animations here quickly. This is the notation I'm using. Blue shows a processor that's off. Its clock it's completely off. 0 active power, leakage power only. Red is a processor that's active. Links that are dark are inactive, that are red are active. These are the two FIFOs, and the color inside the FIFO signifies the fullness of the FIFO. Once a FIFO gets full, this processor is blocking. This is an output stall. If a processor, this is a very unlucky processor, it's also stalling on an input. The FIFO is empty, it tries to read it. The red ring shows it's idle because of an input stall. This is the animation. We see the data coming in up here, flowing through this path. We'll see this is a critical processor here. This whole path is now blocked. All the processors have input FIFOs. They're waiting on this Huffman encoder, and data passes on to this through the Huffman encoder and finally out. This is a very, we see, yeah, the FIFOs going up and down, and then it loops. Our next animation is a much higher speed one. It's our 802.11a. Here what I'd like you to see is the flow of the global data coming through the array in this path. Also, the FFT is broken into 3 butterfly memory pairs. These work from each other because of the memory limitation. So here, again, this is much higher speed. We see the path filling up. You can maybe see here like some of these blinking back and forth. The arrows are a little hard to see in this light, but these work in pairs. And we'll see at the very end, all the processors up here will block on input. Right now, their FIFOs are full. When we get to the end, their FIFOs will dry up, and they'll block on their inputs. I think here we see it. Interesting to note, we see I think the low latency approach to this method. It would be hard to imagine making this a low latency implementation in a single threaded program. Lastly, just a few words on scaling, how we envision this scaling into the future. If we took our exact same design I've shown here, implemented it in 90 nanometer CMOS with a chip a little bit larger than 13 millimeters on the side, we'd have over 1,000 processors, almost a gigahertz, be a teraOP peak, teraOP per second peak, and roughly, depends on voltage and a few things, around 10 to 15 watts application power plus leakage. We envision multi-application systems. So we looked at multitask applications. We can imagine multi-application systems such as a combination video, audio, feature recognition, multiband radio that would have, because we have a homogeneous architecture that allows the very easy ability to map out faulty processors, either at manufacture time or at runtime. Finally, in summary, ASAP's 4 main features are a chip multiprocessor, reduced complexity interconnect and processors, fully independent clocking per processor. We achieve high performance and energy efficiency. The main numbers here, 475 megahertz, 32 milliwatts, 2.4 milliwatts at low voltage. We're able to compute complex multitask applications with varying data patterns and data timing. And we have some tools in development. Lastly, I'd just like to thank the people that made this work possible. Thank you for your attention.
Yes, hi, Henry Baker here. It looks like you can control. It looks like you could control the clocks on each of the processors separately. Is that correct?
Yeah.
But you cannot control the voltage on each processor separately.
Yeah, in this chip we don't. That's correct.
Second question: what is the reconfiguration time?
Reconfiguration time?
Yes.
It wasn't a design parameter that we really attempted to modify, but it's on the order of tens of microseconds.
And what does that involve?
We have a port on the chip, and we have a low speed. It's in its own clock domain, the configuration logic. Oh, I should mention first, there's static configuration, dynamic configuration. So dynamic, of course, is just in this instruction stream. Static is through a low-speed port.
But does that involve which tile is hooked to which tile?
All tiles.
No. In terms of what is the configuration data actually doing?
Oh, it reconfigures the network. In this chip, we have it controlling the clock frequency. There's all kinds of internal parameters.
Okay. The last question is having to do with access to larger amounts of memory and larger types of applications. For example, a H.264 decoder or something like that.
Yeah. Yeah, we have completed work. In fact, this chip was just a few days away. It would have had we have a design for a large shared memory, which is kind of an interesting problem in itself since all these processors are in their own clock domain. But we have that in development, and things go well, it'll be on our next chip. We have designs for a shared memory.
On things like that, how would you handle things like CABIC, which is kind of an embarrassing serial type of an activity?
How would we handle what?
Things like CABIC, arithmetic coding.
Yeah, we haven't implemented that yet, so a good question.
Probably you have usually inactive and active processors on the chip.
Yeah.
And at that time, maybe did you introduce the shutting off systems in inactive processors?
I'm sorry if I understood the question. Shutting off inactive processors?
Yes.
Yeah.
In terms of power savings.
Yeah, it's in terms of the active power, it's automatic. So within 9 clock cycles of a buffer, input buffer being empty or the output buffer being full, the oscillator itself shuts off. So there's absolutely zero active power. They start up again in less than a clock cycle.
Right.
So that much is done. Leakage, this one doesn't address any special techniques for reducing leakage, but that's in our next chip.
Okay, thanks.
Yeah.
Hi, this may be a slightly orthogonal question. So for DSP engineers, if they want to take advantage of all this stuff, they typically design in MATLAB and Simulink.
Sorry, did we design a what?
In MATLAB. They start the design in MATLAB and Simulink.
Oh, MATLAB.
And you showed code in C. I know that there's this discussion going on between what's the right place to do the design. Have you thought about this? And when you're doing this mapping tool, is there any way that people could just come directly from MATLAB or Simulink into your tool?
Okay, good question. So taking a high-level description and mapping it down. So yeah, I do have some thoughts on that. Basically, I feel like this is actually a pretty easy way to map applications. In fact, if you look at the IEEE standard for the 802.11a, they have a block diagram, not a lot different than how you draw a diagram on this hardware. You have block feeding to block, arrows go between the blocks, and a lot of these blocks are much easier to code individually, in fact. So I would say that the MATLAB description, it's convenient in one sense, but you're forcing a naturally parallel application into a serial flow. And as far as automatic mapping, I think that these kinds of designs require some thought into the hardware mapping. I think if you just do it in MATLAB, you're throwing away information. So I see that probably a better approach is maybe designing it in parallel. Thank you.